at the remote sites. NC State.
I don't think that's on.
UNC Asheville.
Hello?
Hello. This is NC State.
I guess they can. Okay, so let's get this started. We are very happy to have Raymond Mooney, who's our first Triangle Distinguished Speaker for this year. He works on natural language processing, machine learning, artificial intelligence, and is now looking at its connections to robotics and code generation and various other things. He is a PhD from University of Illinois Urbana-Champaign. He's co-authored papers on various topics that I mentioned. He's been the president of the International Chair, various AI and machine learning conferences. He's of AAAI, ACM, ACL, and one interesting note, at least in our field, I think we'd like to talk about academic lineages. Ray goes back to Roger Schank, and then to, I think, Danish linguists to German theologists. So, very interesting lineage. Okay, welcome, thanks.
Okay, thank you. I'm very happy to be here. Hopefully the remote sites can hear. We had a little trouble getting the PowerPoint to work, so I've lost a couple of my videos, but I still have some of them. I don't know when you port PowerPoint, so please, your patience for that. Okay, so I'd like to talk today about some of our recent work on generating natural language video descriptions using LSTM recurrent neural networks. So I also have a subtitle for this talk, which I don't think I put this in the released version, but my subtitle is, or How I Learned to Stop Worrying and Love Deep Learning. So I'll explain that maybe a little bit more in a second here. So I always want to acknowledge the many people who contributed to the work. So the number one person is Shubha Venugopalan, who's my PhD student at the University of Texas at Austin, who's the main person behind this project. It's in a collaboration between basically Shubha and I as fundamentally as language people, and a pretty large group of computer vision people across mainly two institutions. Trevor Darrell at the University of Berkeley, where he has a postdoc, Marcus Rohrback, and a couple of PhD students, Jeff Donahue and Lisa Hendricks, and then also Kate Senko, who used to be at the University of Massachusetts at Lowell. She just recently moved as a month ago to BU, Boston University, and a student of hers, Hujuan Xu. So the subtitle. So I'm not known to be a deep learning person. I'm sort of somewhat of a recent convert. And usually I say I didn't jump on the deep learning bandwagon, I got pushed onto it, and the person who pushed me is Trevor Darrell. So the subtitle, I'm a movie person. I love the movie. One of my favorite movies of all times is Dr. Strangelove, which was subtitled, or How I Learned to Stop Worrying and Love the Bomb. So I'm obviously making an analogy here between deep learning and nuclear weapons. You can take that analogy in any other way, any way that you feel put. It's either, let's not go any further on that one. Okay, so a general problem that I've been interested in a very long time, maybe at least 15 years, it actually goes back to my graduate student days in the 80s at the University of Illinois, that my initial interest in this problem was piqued, is connecting language to perception and action, which is usually called grounding language. So most work in natural language processing deals only with text and represents the meanings of words and sentences in terms of words or textual symbols. And I'm a really true believer in the fact that if we're ever going to get computers and robots to understand language truly, it's going to require having that meaning of language tied into perception and action in the world. And so this is generally called the problem of language grounding. So at AAAI few years ago in AAAI 13, I gave a keynote talk there on general, a little more broader talk on grounded language in general. If you're interested, I might direct you. It's easy to find on video lectures. Just search for grounded language learning on video lectures, and you can watch that on tape. So that was sort of a broader. Particularly more recently, I've got interested in the specific problem of connecting language and vision, a particular type of perception. And integrating natural language and vision is an important aspect of language grounding, particularly for human beings. Our main visual sense is vision. So I think my first paper related to this is like 2008. So there wasn't much work back in those days. But recently, the whole area has really blossomed. And Trevor and Kate and I ran a workshop at NIPS in 2011 on integrating language and vision. And Tamara, where she was one of our invited speakers there. She's one of the few people that have been working on connecting language and vision, maybe as long, maybe longer. I don't know. When was your first paper? Okay, you got me beat. But I was interested in it when you were a baby. So, then there have been a bunch of workshops since then. There's a workshop at NACL on vision and language. There's a work on CVPR on language for vision. See, the vision people want us language people to work for them. I don't know if I like that. And then a workshop on co-language and language on vision and language. See, we say and, they say for. There's something psychological going on there. Oh, but then they went to and in 2015, so maybe they've learned the lesson. So it's been a lot of interest in this area recently. The thing that's gotten a lot of attention particularly is captioning images. And again, Tamara did some of the earliest work on this. I have some other early references there. But now it was really last year at CVPR, which means the papers were actually posted on arXiv about exactly 2 years ago, I think. There was a slew of papers, 8 at least from what I remember counting, and it resulted in New York Times articles and PC World articles and all sort of stuff. The picture I gave here is from the Microsoft research version, which I actually was on sabbatical at the time, so I learned a fair bit about their system because I was actually at MSR that fall of 2014, fall of 2014. So it detects words in the image, and it, finds a woman and a holding and a crowd and so forth in this image. And then it generates potential sentences and then uses various pieces of knowledge to re-rank those and pick a sentence for describing the whole image. In this case, we got a woman holding a camera in a crowd. Can he see, based on the bounding box, can he see something interesting wrong about this caption relative to the bounding boxes? One of my students pointed this out. I think I noticed it too. So it says a woman holding. Does the holding involve the woman? See, the holding is over here on this. I guess this might be a woman too, but I think we're probably referring to this. So notice it sort of got lucky. It actually detected a holding over here, but it's really, you think it's describing the one here. So it sort of finds a bunch of words and sort of jumbles them into a sentence, but it's really not deeply understanding that image. And since it doesn't really know which woman is holding the camera. But it got lucky in that case, and that makes a nice caption. Okay, so there's been a bunch of work on images. I started working on video captioning quite a while ago. I forget when our first paper on that was, but for several years I've been working on video captioning, where you get a video, and our initial set that we played with here was YouTube videos. I didn't try this one. Hopefully this one works. This is a funny one. So you want to take a video that you see like that off of YouTube and generate a sentence like a monkey pulls a dog's tail and runs away. So how can we generate sentences describing videos? First, let me talk about this little data set that a former PhD student of mine, David Chen, developed when he was actually doing a sabbatical at MSR with Bill Dolan, who's the head of the NLP group, who was my boss when I worked for MSR. I guess it was Murphy's boss, too, when he did an internship there. He originally collected, they collected 2,000 YouTube videos with 122,000 descriptions in different languages. And Bill was really interested in this for paraphrase and machine translation, not for generating captions on images. But when David came back from his intern there and said he had this data set, I said, ooh, I want to work on that to do image captioning and actually relate the image, the video, to the caption. So the data set's available on that link. And we've only currently worked with the English data, which is the vast majority, but you can see this data set also has descriptions in a lot of different languages. Anyone on Turk was just asked to describe it in their native language so that we made sure we had native speakers, or at least encouraged it by saying, hey, use your native language and describe this video. Here's an example from the corpus. I hope this video works. Not as fun. I had to find a funny one to put on the lead in, the monkey and stuff. And here's 50 human descriptions that Turkers annotated that video with. So you get a little bit idea of the range of different descriptions that come in. Does anyone know one problem the computer vision problem seems to be having here? Usually people notice this. So it's gender, right? Sometimes it's a man, sometimes it says a woman. I think it's a woman. Well, this isn't computer, but this is the person. These are from people. What am I saying? So people are even having a hard time identifying the gender of the person in this. Okay, so everyone knows the big thing these days is deep learning and deep neural networks. So just for those who might not have much of a recent history on all of this, there's a lot of recent success on using deep convolutional neural networks, so-called CNNs, for vision. I guess the main breakthrough there was this 2012 paper. More recently, recurrent neural networks for processing sequences, particularly sequences in language, have become quite successful. So there's this very popular model now called long short-term memory, LSTM, that are recurrent neural networks. So that's RNN is the acronym for that. There's plenty of acronyms here. And there was a paper came out a couple of years ago applying this to machine translation with surprisingly good results. And it really popularized this whole LSTM model. Now everybody's working on applying LSTMs to everything on the planet. We were the first ones to apply it for video to text descriptions. And particularly there's recent work on combining convolutional nets and recurrent neural nets, LSTMs, for describing images. Some of this work, there's some work at Berkeley from my colleagues at Berkeley, also work at Google and other places, came out the same year applying the same technique to the same problem. Of course, there are slight variations. We remained a little bit novel because we were working on videos instead of images. So I'll talk about applying LSTMs to describe video. And there's several others now that have followed up on this, but I'm pretty sure we were the first ones to do it a couple of years ago. We had our first paper in NACL 2015, which means we did it in the fall of 2014. So recurrent neural networks, hopefully people have at least some basic background in neural networks. Recurrent means that you're processing over time. So a standard 3-layer network from the old days of neural net contains some input vector, goes to a hidden state of here I'm calling those the z variables in the middle, and then you generate a set of output variables y from that. In a recurrent neural network, this is called the simple recurrent neural network. Or back in the old days, in the 80s, I remember calling it an Ellman network, because Jeff Ellman was one of the big people that promoted this approach, is you get recurrence by having the hidden unit at time t feed into the hidden unit as inputs at time t plus 1. So here I guess I have a time t, and then it takes input from time t minus 1. So the hidden layer takes as input both the input vector at time t and the hidden state of the previous time step, which then gets copied back for the next time step, and this is why you get this recurrent loops. So this thing has memory now that it can remember things. But the results using simple recurrent networks back in the late 80s and early 90s never really worked that well because the standard backprop through time training algorithms used to train them never really worked very well through these standard known problems of backpropagation called the vanishing and exploding gradient problems. And it was very difficult to train these networks to maintain memory for very long, not sort of in theory, but because of the way the limitations of the training algorithm. So way back in 97, Hochreiter and Schmidhuber developed this thing called long short-term memory, which sort of has some explicit gates that control the memory. I had never even heard of this thing, and I was sort of paying attention to work in this space. But then Google reinitiated the interest in this. I think maybe it was originally applied to speech recognition, and then they applied it to machine translation, and then from there it's just gone all over the place. Everyone and their dog is using LSTMs for every problem under the sun. I'm not going to go into the details of LSTMs and the math. This is just my one quick slide on LSTMs. You have a recurrent unit controlled by 3 sigmoidal gates, and you have these gates, so-called input gate, which sort of in some sense intuitively determines whether the input is significant to remember or have input on the state at that time step. The forget, where you tend to forget, so that circles back how much you used the previous result to get the new one, and then the output gate, which sort of gates the output to the output of the cell. And for various technical reasons, I'm not showing the equations associated with this unit, it works a lot better with backprop and can learn to remember values and learn a better memory for recurrent neural networks. In particular, you can take some input vector and decode it into a sequence using an LSTM. We've found that actually using a couple, sort of in the deep spirit, we actually found stacking 2 layers of LSTM units together is actually helpful. And then you have a softmax on the output, which basically produces a probability distribution across your output tokens. So if I'm doing translation or video to text, these are words. We have a very large vocabulary of words, and it produces a probability distribution over those. And then each time step, each LSTM unit takes the output of the LSTM unit from the previous time step and it generates a new token. So as you run this through time, it takes a fixed input vector and so-called decodes it into a sequence of words or tokens. Then what became popular is using LSTMs to build a particular type of recurrent neural network system called an encoder-decoder sequence-to-sequence model. This MT result from Google really popularized this approach, where we take an English sentence in, word by word. It goes through a recurrent network, time step by time step. Each time step you feed in the next word. And it encodes it into a hidden vector. And you can sort of at least intuitively say that this is some vector that's meant to represent the meaning of that sentence after we've read it in word by word. Then once we do that, we take another RNN, decode that vector into a different language. And that then takes this vector and decodes it time step by time step, producing one word each, into a French sentence. And then you train this network end to end on a corpus of what, MT people, sorry, MT is machine translation, call parallel corpus. The standard initial corpus was from the Canadian parliamentary proceedings. It is published in English and French. You train it to produce the right French translation for the Canadian parliament proceedings from each English sentence, and this network gets trained to be an English to French translator via this so-called encoder-decoder approach, where the RNN is an LSTM. And that paper came out at NIPS in 14. Actually, that summer it was posted on arXiv. And if you hadn't read the paper long before it appeared at NIPS, you were way out of date. So Trevor, one of the LLs here is a guy named Oriol Vignos. He was a student of Trevor. He got Trevor excited about using this framework. Trevor said, oh, we got to switch. I'd already been working with him for several years on video description. He said, oh, Ray, we got to try LSTMs on this. I said, what? And I said, my grad student, while I was at Microsoft, she was actually staying with her husband at Stanford. So I said, go across the bay, go to Berkeley, talk to these crazy Berkeley folks, see if he wants us to do LSTMs for video to text. I'm sure it'll suck. She did it. It worked pretty good. That's why I'm here. That's why I'm, the subtitle of the talk. So the Berkeley group and other groups, that's Oriol there. He did a paper at Google. Simultaneously, several people took a picture in, did an encoding with a CNN to generate a vector, and then used an RNN to decode that into a sentence to do image description in text. Our first paper on this, which I'm not going to talk about, took a video in and just encoded it into a vector by just doing a CNN on each frame and then mean pooling the frame representations to generate a vector for the whole video. This was, I think, a dumb approach, but it got us to our first publication, and we didn't have time to do it the right way and get the first publication on this, and this is critical on this domain. You got to put it up on arXiv. I think pretty sure when we put this on arXiv in the fall of 2014, we definitely put our foot in the sand and said, we did the first LSTM video to text. But we really didn't like that approach. We really wanted a sequence-to-sequence model where you take in frames at each time step, run them through a CNN to get an encoding of that frame, and then have a sequence of frames through one RNN that get into a vector and then decode that into a sequence of words. So it's basically using encoder-decoder to encode a frequency of frames into a meaning vector for that video, and then decoding that, quote, meaning vector into a sentence word by word into English is what we trained it on, but of course it's not restricted. We haven't tried to train it on some of the other data because we have less data in other languages. Okay? Okay, so here's what the model looks like overall. We called it S2VT, sequence to sequence, video to text. So it takes in one frame at a time, takes it through a CNN. That output goes into an LSTM. We use this two-layer LSTM. Each frame comes in time by time, encoding into the hidden state of the recurrent neural network its interpretation of the video up to that point. That's the so-called encoding phase. That ends. We take that vector that comes out of the LSTM, which is encoding its representation of that video, and word by word, we re-decode it into a sequence of words in English to describe that video. Okay, so that's the animation that shows the basic architecture. CNNs, certainly our vision colleagues know more about this than I do. They were originally developed back in the 80s or early 90s. When was the original CNN paper? It was late 80s or early 90s. But again, they became much more popular recently, building these very deep networks of convolutional layers and then fully connected classification layers on top, where it extracts features of larger and larger perceptual fields in the image and then does a classification on those features. And in 2012, there was this famous paper that really did really well on the ImageNet classification problem where you're recognizing objects in images. And since then, CNNs are all over the place. There are even more places than LSTMs. And that's the first step, is to take an image frame from the video, use a convolutional network to encode that into a vector. And we do that in two different ways. One we call the RGB, because it takes the basic pixel values of the image, pumps that through a CNN. We use the so-called VGG16 version of this for this particular system from Simonian and Zisserman. ICLR is a big conference in this area. If you're not familiar with it, it's an international conference on learning representations. We train that first on ImageNet to sort of recognize objects in images. Then we train it on the video. We take frames from the video. We run that CNN on it. This is a standard trick. We take the layer before the classification layer, so-called FC7 layer, which is sort of a featural representation of the information in that video before it gets sent to a final softmax to decide what the class is. But we do the same thing, since this is video, we do this image level processing of each frame using a standard CNN trained on ImageNet. But we also use some techniques out of activity recognition, because this is a video where we want to detect verbs, right? So that's good at detecting nouns in a sort of linguistic sense. We want something that's good at detecting verbs. One of the standard techniques there uses optical flow, which sort of now you process the video to get pixel values that represent how much that portion of the image is changing. Vision people help me here if I'm getting myself in deeper water that I don't know. So actually, Jeff Donahue, one of Trevor's students, included this in their CVPR 15 paper to actually train to do activity recognition on this well-known activity recognition data set called 101 action classes. Where is that from? Who's that from originally? I have the site there. Oh, no. Yeah. Now we also process the video to get optical flow frames, put it through another CNN to produce sort of a deep representation of the video activity information in the video by using these optical flow techniques. And then we pull out that last layer to represent the sort of activity information in the video. Okay, then we train two end-to-end encoder-decoder models, one based on the RGB information, one based on the optical flow information, and then those get ensembled at the final level to predict the best word to produce next to describe that video during the decoding phase. And this is all described in more details in our ICCV paper from last year if you want to know more details. Okay, so I'm not going into a lot of algorithmic and mathematical detail here, but hopefully that gives you the basic idea of how this approach works. So one interesting question then is, okay, we built a system that takes in a video and outputs a sentence describing that video. How do we evaluate this thing? So there's two general approaches we have taken. One is to take the approach traditionally used to automatically evaluate machine translation, where you get a human so-called reference translation for a sentence. You get the system's output sentence that they translated, and then you compare them based on n-gram overlaps in some complicated witch's brew called blue or meteor. Oh, yeah, it is a witch's brew. We found, and several people have found, that Meteor for doing this image and video description stuff works a little bit better than the more standard MT metric, which is BLE. And so I'll mainly present Meteor scores, but I think both of them are in the paper. The next thing we did, I'm a little mistrustful of these things sometimes, so I like to do an actual human evaluation where we give the video and the description to human judges on Turk, and they evaluate it directly, both for how relevant description that is of the actual content of the video and how good the language is, just a grammatical judgment on is that a well-formed sentence in English in our case. So we get relevance and grammaticality judgments directly from humans. Okay, so I'll present some different types of evaluations at different points. So here's just Meteor scores on the YouTube collection that I mentioned, where there's a standard training and test split, with, of course, these are the results on the test data that I did not see at all during training. This was our original old version that did this mean pooling with a VGG CNN, so it's not really taking into the temporal account of the frames, because you could jumble the frames in that approach, and it would get the same representation. Again, in some sense, I wish we never published that paper, but we were pressed for time to get it out in time for the CVPR deadline and put our stake in the ground, so it was good to do. here's something we did that just show that if we just take this S2VT approach and just randomize the frames, how well it does, just to show that it really is capturing something in the temporal sequence, it does that. And then if we actually do the actual sequence of frames in the actual video to do full sequence to sequence, we get, if we just use the RGB input and not this optical flow input, you get 29.2 on Meteor. And then if we put together both the flow and the RGB, I don't have results for just the flow. I don't know if we ever collected that. We get to 29.8, which is not a great Meteor score, but at least shows that all of these systems are doing better and better as we add more stuff to make it a better descriptor. And these are Meteor scores, so it's sort of comparing to human descriptions of that video and seeing how closely the automatically generated video description matches the human description. More recently, there have been some interesting data sets collected for movies using DVS. Does anyone know what DVS is? Stands for Descriptive Video Service. So a lot of DVDs that you buy now have an extra audio track, and if you are visually impaired, you can turn that track on, and it literally describes what's happening in the video to a visually impaired person. And it's a great source. I always have to tell this story. Back when I got a new TV in the early 90s, it had this thing called SAP channel. You remember this thing? Secondary Audio Program. And one of the things that PBS did at the time was they put Descriptive Video Service for the Blind on the SAP channel. And I accidentally turned my TV onto this thing. I didn't even want it. And then all of a sudden, the nature show I was watching on PBS started describing all the stuff that was happening to all the animals that were being shown in the video. And I immediately thought, wow, that would be a great set of training data for training a system that does language grounding. Because even in the early 90s, before tomorrow, I was interested in language grounding. I just didn't write any papers on it. So this is something from, I want people to see this. I am a movie person, so I know all sorts of movie trivia. I think this Queen, this is about, it's a movie from a few years ago. And this shows you, there's a closed caption. Closed caption is telling you literally what people are saying in the movie. The DBS track is an extra audio track, and it has to interpolate between the audio and the actual movie itself, right, to describe to a visually impaired person what's actually happening. So it says, like, looking troubled, the Queen descends the stairs, the Queen rushes into the courtyard, blah, 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 blah. Great training data for training video descriptions that Hollywood has nicely put together for us already. We don't have to Turk anything. Well, that's not it. We have to do some Turking to sort of clean this all up and get it into a state that you can actually give to a video description system. So two groups actually did this a little while ago. The group in Saarbrücken in Germany, the Max Planck Institute, put together 94 movies with 68,000 clips, say about 3.9 apiece, with one sentence describing each of those clips that were extracted from the DVS track of the movie. And then you end up with a set of like 68,000 sentences describing things in those movies. Meanwhile, the University of Montreal put together a data set that has 92 movies. I call it MVAD, for I don't know what the hell these acronyms stand for. You can see the clip length is a little bit longer, a few more sentences describing, but a similar size. So there's two of these similar data sets of clips of movies with descriptions of what's happening in the video for a set of now almost 200 movies. This is a nice new data set. It's been relatively new. It's sort of been a number of people that have exploited this, but I think certainly there's plenty of room to do improvement on all of this. So here's results in Meteor scores on these two corpora. I first put the best prior work that was published by the people who built those data sets and applied the first technique to it. Those are the blue bars there. Here's our approach where we do the stupid mean pool approach, where we're not even doing sequence to sequence. We just cram all the image representations mean pooled into a vector and then decode that. And then here's if we actually do the full S2VT model. So again, we're getting, these numbers are actually quite bad, but we're getting better at least. Okay, so that's a bit of a stop point there. I don't know. I don't mind taking a few questions here. Yeah.
Those of us who are not in this field, something more about these percentages. You said this is related to the description that would be a gold standard?
Right. So I don't know if Mohit or someone else can help me here that maybe knows Meteor better than I do. Do you know Meteor that well or whatever? But these numbers are not huge. So it's sort of like percent match to the human description. There's a complicated formula for Blue and Meteor that does all of this. But it's sort of like as a percentage of how well it matches. So the numbers are pretty low, and that's good to note that these descriptions. But again, there's not just one right way to describe a video. These are a lot of reasons why I like human evals. I don't have human evals right here, but I'll give some later. Well, it's more interpretable, I would say, because you're directly asking human judges on a 5-point or 10 scale. I think we know how good is this a description of this video.
Right, so the problem with these automatic metrics is they just look for n-gram matches between the predicted caption and the human caption. Your machine might have generated a perfectly good caption, but it says it in a totally different way, and we get 0%.
Yeah.
Whereas human
the numbers here you notice is less than the YouTube, because for the YouTube we have 50 what MT people call reference translations, and it actually matches the output of the system to all. See how well it matches sort of all the human descriptions. Here for DVS, Hollywood's only given us 1. So the numbers are really low, because when you run these automated metrics with 1 reference translation, the numbers are low because you have to match that exact person describing the video, not just a person describing. The YouTube numbers, I think, are more meaningful because it's 50 humans, and now we're matching that on 50 humans rather than 1.
So it's an average across 50 captions.
But we can have huge debates about the value of these automated metrics. They actually are incredibly useful when you're building systems, I think, to show whether you're making progress. But at the end of the day, I actually like to see human evals, and I have some later. Okay. So more recently, this is actually a paper that's been out for a while, but it's not yet presented. So EMNLP, one of the major natural language conferences, is in Austin in 2 weeks. I got to get back from here to go to it. I never like going to a conference in my own hometown because I got to run back and teach my class and then run back to the conference. But I'm going to welcome all my natural language processing friends to. And so we have a paper there. And I thought it was appropriate for a language conference. Can we say, how can other linguistic knowledge help us improve video description? In particular, we know a lot about mining knowledge from text at this point. How can we integrate 2 things that we know how to do well, which are distributional word embeddings and language models trained on external text? When you build an MT system, you don't just use parallel data English-French. You use a whole bunch of just French and English monolingual data in order to do translation back and forth between English. And so we've tried to apply some of these ideas to video, to text. So the idea here is in the decoder, we're going to exploit a lot of just taking knowledge of language statistically analyzed from Wikipedia and GigaWord and all these big text resources to build vector-based representations of words and language models. And I'll just talk briefly for those who are not coming from the NLP world what this means. So we use distributional embeddings, and particularly when you encode the word into a neural net or decode it, you use what's called one-hot encoding, which means you have 1 bit or 1 neuron for each word, and then the value on that neuron is the probability that that's the word. So it's a very so-called, what in the old days we call localist encoding. We now have lots of ways of building up distributional representations of words. We use this system called GLOB that comes out of Stanford, which is a derivative of Word2Vec, if people know Word2Vec out of Google. I'll talk just very briefly more about that. We also use what language people call a language model, trained on tons of just offline text. And I'll talk a little bit more about that. And of course, we get the best results when we combine both semantic distributional representations of words with this so-called deep fusion approach to doing language modeling, which I'll get to in a sec. So distributional embedding, for those of you who don't know it, we take a word and encode it in a vector in some reasonable size space. And everyone who starts with, you have to start your description of this with this quote from this linguist Firth from 1957, who said, "You'll know a word by a company it keeps." So it builds a vector, a dense vector. 1-hat just says one bit 1 in this huge vector. Here we're going to have a dense encoding where we have continuous values across all of our vector elements that capture and represent the meaning of a world as a point in a dimensional space. And the idea is that it trains that on text so that it encodes what context that word appears in. And if 2 words appear in very similar context, they'll end up in very close points in that space. And this has literally been going on forever. One of the earliest approaches was called LSA, if you heard of this, latent semantic analysis or indexing. And then recently it's really blossomed into things like Word2Vec. We use this pretty state-of-the-art technique called GLOB to do this. But it gives you a vector space in which similar words and meaning have similar vectors, where the 1-hot encoding doesn't give you that at all. And hopefully the neural net can exploit that to have a sort of deeper representation of the meaning of the word. And that meaning has been statistically mined from huge bodies of text. I think we use all of Wikipedia, or some dump of Wikipedia, and GigaWord, which is a large standard data set of a bunch of news articles and all sorts of other stuff. Language modeling. This is the first thing you teach in an NLP class, right? So It's just a model that you give it a sequence of words, and it says how likely that sequence of words is a grammatical, meaningful sentence in your language. So here I give you an example. Say I have this, a man is talking on a phone. That's a sentence from that example I gave. Hopefully it would give that a very high priority. That's a very reasonable sentence in English. Well, maybe a little bit less common, but still reasonable is a man is conversing on a phone. But what about a man is tapping on a phone? That's a little less likely. Then we get to man is sitting on a phone. That's even less likely. Then I tried to come up with something totally bizarre. This is the best thing out of the man is flying on a phone. So it assigns a probability. It would say this a priori is a bizarre description. Don't use it, basically. This is a very likely description a priori. I'm not looking at the video at all. I'm just saying how much sense does this make as an English sentence? It gives a score to that. So these are techniques that have been used in speech recognition for 50 years or something, 40 years anyway. But the current best techniques use what? They use deep learning. They use LSTMs, in fact, actually giving the best model. So just a real quick slide on this. You train an LSTM to just take a word and predict the next word in the sentence, is standardly what a language model does. Here, this just means beginning of sentence. So you train this model, and it ends up now you can actually put a sentence in then. It'll tell you how likely what's the likelihood that model assigns to that word as being a sentence in English. And LSTMs are pretty good state-of-the-art now language models as well, which is another reason why they're popular. But how do we integrate a language model that just looks at text with a translation model that looks for converting video to text? We tried various techniques. You can read the paper for other things we tried. We saw this thing called early fusion, late fusion. We tried various approaches. We landed on this approach we ended up calling deep fusion. It's actually pretty closely related to a technique that's been used in NMT. NMT is a new acronym, Neural Machine Translation. It derives from the whole Google work on using encoder, decoder, LSTMs for machine translation. We think our approach has some slight advantages, but I don't want to get into that. What we do is we run simultaneously to generate the sentence. We run a language model to predict the next word, and we run the video to text model to predict the next word. We then concatenate their hidden representations and then use that as to go into the softmax function to predict the probability of the word. So it sort of learns how to combine how grammatical the sentence would be if I added that word versus how descriptive that sentence would be of the video if I added that word. I think it's a fair way to describe it. We tried other ways to integrate the language model into the translation model, but this seemed to work the best. This thing is trained on a whole bunch of text. Like I said, here's Wikipedia, UKWAC, BNC, GigaWord, a whole bunch of MS Coca. We found it useful to put in some sentences that are actually descriptions of images. We don't have huge repository descriptions of videos. I mean, the whole system gets trained end to end on the video corpus. But it helps to add a little bit of just image description data we found. So it ends up with a pretty large vocabulary of 72,000 words that it can use. And we've trained the glove model on this sort of combination of Wikipedia and GigaWord. So these are all pretty standard techniques, but how do we integrate this? The deep fusion is a little bit of an innovation, how we integrate that into a video to text system. So then here's some results. Here I actually have blue and Meteor. I think the Meteor is probably a better thing to look at. You can see the blue scores are actually higher. But things get better when you add more good stuff, So this is our basic model, the STV. If you add the deep fusion approach to adding the language model, it goes up a bit. If you add the distributional word embeddings, it goes up a bit. And if you put it all together, you get the best results. So said by adding both distributional information on word meanings that we get from mining text, plus sort of grammatical and sequence information about language that we get from building a language model from a large body of text, we can improve the descriptions. Now here's where I'll present some human evals. So we did two human evals. One is we give the Mechanical Turk worker the video, and we give it the set of sentences describing the video from different systems and from the human being, and ask them to rate, how good a description. We tried, I think, different instructions to our Turkers. I didn't put those up here, but just rate it on a scale of 1 to 5. A sort of Likert scale is usually called, the least relevant description of the video to the most relevant. We also wanted to rate how just good sentences are these, irrespective of the video. So here we don't even give them the video. That's what this X to the video means. We just give Mechanical Turkers a sentence and say, rate how grammatically meaningfully correct sentence this is in English from incorrect to grammatically correct. So here's some numbers on the YouTube data. Here's our baseline S2 V2 model on relevance and grammar on that 5-point scale. Here's if we produce the full combined model, includes both distributional word embeddings and LSTM language models. What I've put on here to give you a baseline, this is what the human gets. So you can see that his scores, grammar were actually pretty close. But on relevance, still we are not at human level performance. I was talking to several people today that I try to fight the hype in deep learning, that we've made a lot of progress, but we have not solved all the problems in AI with deep learning. So, the algorithms are getting better and better, but we're not at human level performance. Humans getting 4.5 on this scale, and our best algorithm is just getting 2.24. So I like to be honest about that. That's out of a 5-point scale. So here's some, one thing I learned from the vision community I like. You always show examples where your algorithm works, and you show examples where your algorithm doesn't work. So there's a standard term for calling examples work. You say you're cherry picking, right? So I call these cherries. But I actually did a coinage here. I'm trying to spread my linguistic innovation. I call the ones where your algorithm doesn't work lemons. So you're lemon picking instead of cherry picking. Everyone should use this terminology. I'm trying to spread. No one's going to remember me except I innovated this terminology for presenting where your algorithm works and where you don't. So what this shows is the voice will come out with the generated algorithmic description. If you want to, you can read the gold standard description. It's not very legible here. I should have had Shuba do this in some, well, it depends what the background is. It's hard to get a color that is always shines. Yeah?
By lemon picking, do you mean the very worst that your system did, or ones that you think are somehow humorous?
No, it's meant to be very used. I have ones I call sweet lemons. At my sweet lemon video, no, they're just wrong. Again, my grad student made the choices. I just tell her pick some cherries and lemons. Anyway, well, we can send you all the output. You can pick your own cherries and lemons. I showed you the quantitative numbers. That was a scientist. Now I'm doing marketing. Give me a break. But I'm doing honest marketing because I'm showing you lemons.
A polar bear is walking on the snow. A woman is mixing ingredients in a bowl. A man is performing on a stage. A monkey is playing with a man.
It's a chimpanzee. It's not totally cherry. Chimpanzees are not monkeys. Oh, the human thinks it's a monkey. Well, we want to do better than humans. We want to know the difference between chimpanzees and monkeys. So here's what my grad student picked is lemons. No,
a man is running down a wall.
I mean, they're not totally crazy.
A man is holding a woman.
I don't know, what the hell is that video from?
A group of men are dancing.
I had some cute examples that we called sweet lemons, but for some reason when we ported this, when it wasn't...
A tiger is playing with a cat.
Well, you can imagine what the videos are? I don't know.
A woman is doing an exercise.
I don't know.
A baby is playing with a toy.
Anyway, we can't see those videos. Yeah. Here are numbers from the movie corpora, meteor score. Here we could not show the video to human judges. Why? Damn lawyers, right? IP. So we didn't really have IP access to these videos to show them to Turkers. So I don't have relevance scores because we couldn't show Turkers the video and the captioning legally or something. I think Shuba decided we didn't want to go there because there could be IP issues. Damn lawyers. But these are meteor scores. The grammar goes up quite a bit by adding the linguistic knowledge. So the sentences it's composing, here it's clearly going up a little bit in relevance too, because if you make it coherent from a linguistic point of view, it's also more likely to be descriptive. And so the grammar scores go up quite a bit. Same thing on this other movie corpus, the MVAD corpus. The grammar scores here aren't quite as good as the other one. I don't know why. That's like the big gap between 4.1 and 3.3. Not sure I don't have a good idea of what the distribution difference is. I showed you there's some stats are a little bit different about the length of the videos and things. These videos were not working either, unfortunately. So these were the cherries for the movie data. The cherries weren't running, but the lemons were. So you just get to see the bad output from the movies.
Someone grabs the phone and punches it at someone. Someone sitting on the bed. Someone watch the news. Someone sits on the couch.
I think it's
someone glances at the boy.
I don't know.
Someone is sitting on the stairs.
that's sort of understandable there, what's going on. There's stairs and there's a man sitting, but the man's not on the stairs. So I'm sorry, I mean, somehow the video wasn't working for my laptop, and we ported these videos. Some of them got mucked and some of them didn't. I hate all this technology stuff. Why did I become a computer scientist? Yeah, so how am I on time? Actually, that's actually pretty good. Well, I should have had more time playing videos, but some of them didn't work. So just to wrap up, I really am a big believer in grounding language and vision is a fundamental problem with many applications, and no one's more excited than me the fact that the field has grown so much over the past few years. You know, a few years ago it was just a few people in a room in Granada, and Tamara and I were there, and we were all enjoying each other. But now we're in the New York Times, and all this stuff is going on, and Google is putting up stuff on the web and describing African American men as gorillas and getting in trouble, and so you know we made a lot of progress in some ways, at least. But it's a really exciting time over the last few years, and I can imagine it will continue for a few more years of this whole bringing of language and vision together. The one thing I wanted to talk about here is, for those who don't appreciate, the community is really split. There are language people like Mohin and I who go to ACL conferences and language conferences. There are vision people like the Bergs that go to vision conferences, and we hardly ever talk to each other. And now we're really in bed together and working together, and it's been great. You know, that I think the combination of insight from both the vision community and the language community into this work, we now have tightly integrated teams that really use both language expertise and vision expertise to build these systems, and no one's more pleased about that than I am. I think it's really great. And we still have a lot of room, as I showed you, we're not matching humans yet. People who did the image description, there were results on there that they were claiming that their algorithm was doing as well or even better than humans at describing images. Take that with a grain of salt. MS COCO is a very limited data set, has certain objects in it, right? It's sort of a select distribution. These are really much more representative, I think, of things in the wild, and our numbers are not matching humans, and you can try yourself. I think we're still in the lead on this. I think we're not quite in the lead on YouTube anymore, but there's been some competitions. We won the best competition in the movie description thing this past year. So it's not like I'm presenting results that aren't state of the art. They are, and the state of the art is not human equivalent. So we've developed these broad preliminary systems that describe videos using a combination of convolutional deep neural networks and long short-term memory recurrent neural networks. Two of the problems that I'm excited about working in the future, all of these systems take a pre-segmented clip from a video and generate one or maybe two sentences describing it. How do we take the entire movie, segment it at the proper points into clips, and generate descriptions simultaneously? So this is the thing I've told Shubha she needs to try to do before I'll let her graduate. We're going to just train the LSTM to predict the clip boundary. So we're just going to run the LSTM on the video frames and have it learn to predict where the clip ends, and then it will generate a sentence for it. And it'll keep going until it thinks it's worth describing again. It'll generate an end clip, and it'll put out a sentence. So we'll see how that works. No one, as far as I know, has done both video segmentation and description simultaneously, jointly in the same system. And that's what I'm hoping Shubha can at least take a first shot at before I let her out in May. The next thing I'm excited about, I mentioned that to some people here, since this is a graphics department here at UNC, I want to get out of language and vision. It's too crowded. I don't want to be in the New York Times. I want to work in obscurity in the academic ivory tower. So I want to move into language and graphics. And I want to do the reverse of what I've been working on for the past 5 or so years and generate animated videos from language. And so a new member of our faculty, Shixing Wang, who works at the intersection of graphics and vision, and I have been having some fun initial conversations about how to do this, possibly using deep learning technology like LSTMs to generate animated graphics from language. There's been some work on generating static images from language, in particular Angel Chang, is that right? At Stanford, one of Chris Manning's students worked on generating static description 3D scenes, static scenes from sentences. We want to move to making that animated video from sentences. Okay, so I think I'll end there.
So I think I'm supposed to take questions from the remote sites first. Any questions from NC State, Duke, Asheville? I think those are the 3 sites.
Yeah, I've got a question. Can you hear me?
Yeah.
So is there work to also incorporate audio data from these video clips? Seems like that would be an important piece of the puzzle.
Yeah, so that's a very good question. Shuba's back, hopefully in Austin, busily working exactly on this problem. We had to get the audio for the movies. So we're going to be able to get this from the German group because we work with them. And so we're in the process of getting that. And there has been, I have not read this literature myself, but my students looked a little bit. There is work on using LSTMs for audio processing. So the idea is we just feed it in as another input into the, in particular, I think this could be useful on segmentation, particularly for these DVS things, because when you're doing DVS, you have to not even take into account what's in the video, because you have to stick this in audio into the audio track. So anyway, so yes, I think that's a very interesting problem. We're just starting to work on it, but I can't say anything concrete about it. It'd also be interesting to put in the closed caption track too, possibly. We haven't tried that.
And audio also, not just for speech audio, but specific sounds that can help you.
But audio will give you all of that, but the CC will give you the text version of the speech.
Specific actions have specific sounds. Any other questions from remote sites? Okay, I'll take local questions, but feel free to interrupt if remote sites have questions. Any questions here? Yeah. And
now your question, in the simulations, or I guess the results that you showed, how long?
I was just wondering how long does it take to?
Ooh, this is the question where you need the grad student there to answer. So yeah, I'd have to get back to you on that. I don't think it's like real time. Yeah, I don't really know. Yeah, that's an answer I should have. It was really nice when I gave a version of this talk at Stanford because Shuba was actually there visiting her husband, so she was in the audience. So I get one of these, and I just go, yeah, Shuba, what's the answer to that? She's not here. Hey, I can call her. It's like call a friend, you know.
Remember around 7 hours.
7 hours for the whole data set?
Yeah, for YouTube data set.
And how many is YouTube? What's the size?
It's 2,000 videos.
On test set?
On test set it is around 1,200.
So 7 hours divided by 1,200 per video.
Yeah, so a student here has actually been following up on some of this in our class project in Mohit's class. So yeah, thank you. You need good GPUs to do this stuff. I assume everybody knows that.
Yeah, Alex.
So at some point in the talk, you were talking about combining predictions at the level of words. You have your word from your translation model and your word from LSTM.
Yeah.
And
so it's just a weighted sum of the output of the softmaxes, and we train that weight on the development set.
And so the question is, do you think that words are the right level to be combining the outputs?
Yeah, so I think we played around with, there's all sorts of ways to do these fusions of various sorts, and I think Shuba did look at different ways of doing that, of doing the ensembling of the optical flow and the RGB networks, and that, yeah, so yeah, there are definitely other ways to do it. I think we played around with that a bit, but it certainly didn't do a comprehensive study, and I agree with you, that's probably, because, you know, the deep fusion works best for the integrating the language model into the system. That we did do. We did a more systematic study there. But how to integrate the flow and the RGB, I think there could be some more investigation of the best way to fuse that information, but that's a good question.
Yeah.
Does your approach give just the most likely caption, or can it output, say, a spectrum of possible?
Yeah, so you have to do a beam search, but you can generate the top end captions approximately by doing a beam search through the output of the LSTM. There's some interesting computer science questions there in terms of doing optimal decoding of top end hypotheses. Maybe even Mohit might know more about this sort of thing than I do.
So yeah, there's the standard beam search approach where you basically maintain a beam of the best option at every time step, and then this expands into the next beam, but then you chop it at the top K. But then there's some interesting research on how to take that top K list and then maybe re-rank it with some global features, because now you have the whole sentence. Yeah. So you can have some global features looking at the whole sentence at a time and re-rank those options instead of one word at a time.
So if you get multiple outputs, does that improve the performance according to the whatever measure?
Sure. I mean, yeah. So I'm sure it would. I mean, but then how do you score this? I mean, if you say take the best out of the top 10, I'm sure the numbers almost are guaranteed to go up, I guess. But yeah. But you know, like there's this whole body of work. I've done work in semantic parsing to do this so-called global re-ranking, which was what Mohit was referring to, where. So we haven't tried those techniques. Those are standard additional techniques to sort of clean up the output of these sorts of models, and we have not explored that space. The Microsoft thing I showed, because they do some pretty global, because they use a whole bunch of stuff in there. They do that final step on that last box is a global re-ranking. And I don't know anyone who applied that to video, but again, that's another standard trick from the bag that you could apply to this, and you probably get another boost of 1% or something.
Any other questions? Yeah, Kate.
So we are using optical flow, basically motion information, to infer the captions for videos or images. How sensitive is your model to the accuracy of optical flow? Because from a geometry perspective, optical flow is very, very hard to estimate accurately.
You're out of my space here. This is vision people questions. I'm a language learning guy, so sorry, I don't. Yeah, I mean, we use some out-of-the-box techniques for doing the optical flow.
Yeah,
and I'd have to consult
my... For videos that is out of the, for example, video clips from movies or other like online videos, the optical flow field you get is probably very noisy.
Yeah. Well, again, neural nets are pretty good at dealing with this sort of noise and training to not to overfit it.
I'm saying the actual information you input into your network basically gives you maybe not reliable, even wrong motion estimations. So you're kind of inferring something from totally nonsense motion information.
I don't think it's totally nonsense, but it's certainly I'm sure that it is noisy. Well, give me better tools for extracting optical flow and I'll plug them in. This isn't my fault. I'm a language guy.
Yeah, I mean, actually, there's some very interesting scope in doing this jointly, right? So can optical flow be improved using information from the text and vice versa, right? So maybe there's an interesting project in improving optical flow using descriptions in text, because it's telling you where the actions change and where does the object focus change.
So we use whatever the Berkeley Vision Group recommended for this. I'm tossing that one to Trevor and his group.
Any other questions? Yeah, Dinesh.
So you mentioned that you're looking into audio cues at the end.
Yeah.
Is it audio only or audio plus video? I would guess that humans.
No, we're just adding it. We're not taking anything away. That is to add the audio to the visual input.
So mostly video plus audio, or are you getting an equal weightage, or some are you getting the two?
Oh, again, how you fuse stuff is complicated. You can try all sorts of different ways, but we were just initially just going to try and put it in equal weight. But yeah, I mean, how to fuse, this gets on to this multimodal fusion. I gave a very early version of this talk at a nice workshop at MIPS not quite a year ago in December in Montreal last December on multimodal learning. Very fun workshop. There's a lot of people working on different. I also do stuff in learning for robots, and we're even fusing haptic data from a robot arm with vision data. I really think fusing multiple modalities that's why I like adding the audio in, because I'm a big fan of not just language and vision, but multimodal broadly construed.
One question is right now I think in image capturing they involve to a VQA, video question answering. Have you tried something?
Yeah, so it's interesting you mentioned that, because I'm working on a new grant proposal, and one of the participants is Antonio Torralba at MIT, and apparently has this new thing called movie QA or something. So yeah, so Debbie and Drew have developed these nice test sets on visual question answering from images, and Antonio has at least some initial set of data that I haven't read the paper. Someone read his paper on this? Movie QA it's called or something?
It's Toronto, right? From Sanya, and it's more Sanya and Raquel at Toronto.
Oh. Well, Antonio's something.
Yeah, he's on it too.
Antonio
okay, I'm sorry. He's the guy I'm talking to, so I didn't read the paper. Sorry if I'm skipping a bunch of his co-authors.
No, yeah, it's actually
sorry. Yeah, so I haven't read that paper yet, but I think I like both the VQA task, the movie QA task. I've been the obvious person to get into VQA, but so many people jumped on that boat. It was like, I'm going somewhere else. It's crowded. So there've been a lot of people competing in VQA. I don't know who would you say the best group in VQA is?
Right now it's Trevor's paper.
That's right. What's his name? He won best paper. Look at the best paper award at ACL. What's his name?
No, that's old now. So that was that was Jacob's.
Yeah, I was published 2 months ago. That's totally.
So there's the need. So because related to the next question, there's this multimodal bilinear compact pooling idea where if you're bringing in multiple modalities, there's an important step in between where you should bring them to a joint space.
This whole area is so fast moving. There's probably someone published better results while I was giving this talk and posted it on archive.
Yeah, but the good thing I think you said is all the collaboration. I didn't even know, I forgot that Antonio is on the paper. So it seems like...
I didn't know about Movie QA until just a few days ago.
But I think the problem with that data set is people think it's too challenging, it's more futuristic. It's like understanding the whole movie, not just the questions, but the cultural context and the whole story of the movie. So there might be scope of a
Yes, right now you have to rush to be the first person to publish crappy results on a challenging problem that's way beyond what we can actually do.
Any other questions? Okay, let's thank the speaker again.
Thank you.